Iceberg with Flink at DoorDash. My name is Nate, and I'll be your moderator for this session. Just a heads up that we will have a time for a brief Q&A after the presentation, so be sure to use the Ask a Presenter tab to ask questions and engage with your fellow attendees. With that, I would like to welcome our speakers, Tristan and Gaurav with DoorDash, to the stage. Guys, take it away.
Cool. Thanks. Welcome, everyone. My name is Gaurav Sharma, and I'm joined by my teammate, Tristan Culp. We work on the data mobility team within the data platform group at DoorDash. Today, we're excited to talk to you about how we integrated Iceberg with Apache Flink at DoorDash to kind of improve our real-time streaming solution. So here's the high-level agenda for what we're going to be talking about today. We'll start with some historical context about what the real-time streaming platform is, as well as a quick intro to Apache Flink and how we leverage it for our use case. We'll also cover kind of our existing architecture pre-Iceberg and what challenges we faced and what kind of led us to Iceberg. We'll then cover kind of our transition to Iceberg and what changes we made to kind of make the new architecture possible. And then we'll go on to some observed benefits, as well as challenges we faced and learnings we've kind of collected and would like to share along the way. And we'll finally wrap up with some future plans and answer any questions. With that, let's jump into the background. So yeah, what is the real-time streaming platform, right? So it's basically an in-house built platform mainly used to process application events in real time. So these application events are telemetry events that are coming from either DoorDash web and mobile clients. So this could mean either, customers, dashers, merchants, and so on. Or it could even be from internal services within the DoorDash engineering ecosystem. So these events are each have kind of like a unique downstream table in our data lake or data warehouse. And the streaming platform essentially processes each unique event that comes in and writes the data to its respective table in the downstream data lake or data warehouse table. This data is then available for our downstream consumers to use for any of their use cases. So just to talk a little bit about scale, at our peak traffic time, we're looking at more than 30 million messages per second coming in. And some of our highest volume events produce up to 5 gigabytes of data per second. So the overall mission of our platform is to provide our data users and applications kind of with the capability to capture, access, and create real-time insights, right? So a lot of our downstream users have critical use cases such as real-time ML feature generation, critical ETL dependencies, and so on. And a lot of these require very low latency and near real-time data availability. So kind of given the low latency requirements and the massive scale we're working at, how is this actually possible, right? And kind of the central tool around all of this is Apache Flink. So to do a quick intro to this, it's essentially an open source framework for both the distributed stream and batch processing. For our use case, we use Flink for stream processing since we have unbounded data coming in at any time. So we'll focus on that aspect. Flink suits our use case pretty well since it's ideal for low latency and high throughput use cases. Another benefit is it's stateful and fault tolerant, right? So in the case the Flink job fails, the job actually periodically checkpoints its state. So in the case of a failure or restart, we're able to resume from where we were processing the data last to avoid any type of data loss. Flink also comes with a lot of out-of-the-box data source and sync connectors. Source meaning simply where we're reading the data from, and sync meaning where we're writing the data to. So it comes with a lot of connectors right out of the box to easily kind of plug in to be able to read and write from various sources and syncs. Yeah, so now I'll go a little bit into how we use Flink in our real-time streaming architecture. So there's a very detailed blog about this in the DoorDash tech blog. We won't do a deep dive into that for the purpose of this presentation, but I've included the link here. On a higher level, you can see our applications generate telemetry events, as I had mentioned before, and they basically produce the data to Kafka. Our Flink applications consume the data from Kafka and then produce to S3. So from S3, our existing architecture or historical architecture had used Snowflake as a data warehouse. So the way we kind of load the data from S3 to Snowflake was via a Snowflake offering called Snowpipe. Snowpipe internally uses SQS, an SQS notification to kind of notify when there's new data available for ingestion. And the Snowpipe will essentially just ingest the data into Snowflake. And this had been kind of our working architecture since like the inception of the real-time streaming platform. So what are some issues and challenges with this, right? So the main issue here is our Snowflake costs spiked with increased platform adoption. So I'd mentioned that our peak traffic right now is over 30 million messages per second, right? When the platform initially started, we were looking at more, the hundreds of thousands of messages, so much smaller scale. As the adoption grew, the scale grew, and the size of the data we're processing, grew astronomically. So with that, our costs kind of spiked uncontrollably. Snowpipe data loading could also be seen as a bit wasteful, right? Because we're writing the data twice. The Flink application is writing it once to S3, and then again, the Snowpipe is writing it again to Snowflake, right? So we're double writing the data. And also around this time, the data lake solution kind of became more popular in the industry around this time. It kind of represented a step towards vendor neutrality and was a bit more efficient in terms of the data, right? So this is kind of where we began exploring data lake solutions, right? And the first one we experimented with was Delta, since DoorDash has had some experience across other teams with Delta Lake. So we actually did set up Delta Lake kind of pipeline for the real-time streaming architecture. And we used out of the box the Delta Flink connector. So we did run into some issues with the Delta Flink connector, which led to some cost and operational issues. So it wasn't a completely smooth process for us, and our jobs were a bit unstable. And we had to sometimes over provision resources such as CPU and memory. So kind of these were the issues we were running into with our Snowflake architecture and also our experimental Delta architecture. So that kind of brings us to the world of Iceberg, right? So why Iceberg to begin with? So Iceberg had a more mature native integration with Flink. Like I mentioned, Delta, we had some issues, running with the Flink connector, and it makes sense, right? Delta is a bit more Spark centric and a bit more focused on that. And at the time, Iceberg definitely had a much more mature native integration with, a larger community of support specifically for Flink as well. It also had some rich features such as highly flexible schema and partition evolution, which was pretty appealing to us since we could update the schema or partition on the fly without having to rewrite the entire table's data. Concurrent table writes was another pretty interesting feature to us since we had potential use cases for this, such as backfilling an event table while still maintaining the live ingestion. You could have like dual writers, which would be pretty useful. And overall, the fully open source kind of with community driven support and development, this was definitely a big pro for us since there's a wide range of contributors from a lot of companies. So I think kind of that large kind of community driven support was very appealing to us as well. So with that, we migrated to our solution to use Iceberg. So here's the high level architecture using Iceberg. So not a lot has changed with the real-time streaming platform itself. We can see applications still produced to Kafka, and we still have Flink applications consuming the data from Kafka. But in this case, they're Iceberg Flink applications, and that means they're writing to S3 in Iceberg format. In front of the raw data, we have AWS Glue as our data catalog or metadata management service. And we have, query engines such as Trino, which use the catalog and so our downstream users can query the data. One thing to note here is we're pretty highly integrated with Snowflake. A lot of our ETLs and tables are already in Snowflake, and Snowflake does have very powerful querying capabilities. So because of that, it is very crucial for us to maintain the ability to query Iceberg tables from Snowflake. So kind of our solution to that is using Iceberg external tables, or otherwise known as unmanaged Snowflake tables for Iceberg, right? So that means that Snowflake can access or periodically kind of sync the AWS Glue catalog, and users can still use Snowflake to query Iceberg tables. Although we can't write to the table, we can we have full read access, which kind of satisfies our use case, since our real-time tables are append only, and our users have no need to kind of write to the tables. Now, I just want to quickly go over what kind of changes were necessary from the Flink end to kind of integrate with Iceberg, right? So it's actually very minimal changes needed for this. So a Flink application consists of 3 layers, right? A source, a transform, and a sink. The sink layer simply, reads from a specific data source. In our case, it's Kafka. Transform applies any modifications, edits, or transformations to the incoming data stream. And the sink simply, uploads or writes the data to the downstream destination, which in this case is S3. You can see down below with the Iceberg Flink application, not much has changed. We actually don't need to change the source layer or the transform aspect of the data stream. The only thing that changes is the sink, right? We're writing to S3 still, but with the Iceberg format. And Flink has, some nice out-of-the-box connectors for, writing to S3 with like an Iceberg format. So it is pretty minimal code changes needed in that aspect. Only the sync function had to change. There are some more nuances, which we'll discuss later in the challenges section. But yeah, overall, it was a pretty seamless migration from the Flink aspect. Yeah, so now I'd like to dive a little bit into the benefits from moving over to Iceberg. So here are the main kind of high-level benefits we'll cover, right? So the big one here is cost savings. We'll also talk about increased reliability, operational burden improvements, and also cover data lake availability as a whole. So looking at Flink application cost savings here, we immediately saw a 25 to 49% storage cost reduction compared to kind of our original Snowflake architecture just by using the default ZSTD Iceberg compression. So this is when we're uploading the data. When Flink is kind of writing the data files, we're seeing a significant decrease in cost, S3 storage cost when we're writing these files, just from that default compression. And then another thing to highlight here is the compute cost reduction compared to the Delta format, right? So as I had mentioned before, we actually had to over provision our Delta jobs due to some issues with the Delta Flink connector, and because of that, we incurred higher compute costs. And you can see here, this is an example. This bar chart is an example event for which we have a Delta Flink job and an Iceberg Flink job writing data. And we can see a 40 to 70% cost reduction overall from switching to the Iceberg Flink application versus the Delta format one. So significant cost savings in the storage and compute aspects for the Flink application. Another thing to highlight here is the significant Snowflake cost savings. Right, so one feature we really appreciate here is the ability to query Iceberg tables from Snowflake. As I mentioned, we're using the unmanaged table solution. So the Iceberg support with Snowflake is pretty substantial there, because with this unmanaged table format, we're still able to query from Snowflake, but now we're able to completely remove the Snowflake storage costs, right? That double write that I mentioned is no longer present since we don't have to write to Snowflake. And kind of, I would say the most expensive part of our original architecture was the cost of actually ingesting the data via Snowpipe, right? So that cost is removed as well. The only kind of remaining cost from here is the cost to periodically sync the Iceberg table with the unmanaged table. But you can see like the cost of the cost of doing this sync is significantly less than if we had actually ingested that data into Snowflake via Snowpipe. So there's significant cost savings we've realized here, and in fact we've saved in the orders of millions, many millions of dollars from just migrating some of our highest volume events from our original kind of native pipelines to our new Iceberg format pipelines. Yeah, with that, I'll hand it off to Tristan to continue with benefits and the rest of the talk.
Thank you, Gaurav. Yeah, that was great. I'll continue from here to talk about some of the remaining benefits that we saw and then talk about the challenges. So, yeah, another benefit that we saw from adopting the Iceberg format was just a general increase in reliability. And we have some items listed here that I'll talk about. So, like Gaurav mentioned earlier in the presentation, we tried adopting Delta with Flink originally, right? But Delta has this concept of a global committer. And at the time with Flink, this solution was not really working for us. We were in talks with Databricks to try and get help, and we did receive some, but we still had to maintain sort of an over provision of resources so that we would not be constantly alerted or paged by problems with the Delta global committer. So moving away from that concept and into Iceberg with Flink allowed us to reduce the amount of provisioning, which lowered costs, as well as reduced the number of problems that we faced when working with our Flink jobs. The next item here is talking about how, yeah, the key features that we were drawn into was the concurrent table write support. So this sort of guarantee of reliability means we don't have to worry about writing to the same table from different sources. So we can have real-time streaming pipelines along with backfills going on at the same time, or this even opens up writing multiple pipelines to the same table. So this sort of capability is a good improvement for our reliability as well. Lastly here, a key feature that we really enjoy actually is the snapshot time travel capabilities. So previously, when we were working with Snowflake warehouses, we would have problems with the table state or the quality of some of the rows, and we would have to reach out to a Snowflake representative, open a case, get help from them to recover an older table state. And I believe that they also do have this time travel capability, but that's an additional paid option. So having the snapshot time travel, one, out of the box, two, open source, and we can own it, we can manage it, very helpful and really help towards our reliability. Yeah, move on to the next slide. Yeah. So another benefit was just in general the move towards our data lake first approach. So adopting Iceberg really helped us increase the availability of our tables in Data Lake. Like I mentioned, when we were working with Delta, we had started adopting it for a few jobs, but we were facing a lot of troubles. When we started with Iceberg, we actually were able to let this natural growth occur where any new events that are created are going to be created with Iceberg format, and any of most of the very high traffic events we can target first in these migrations to get the biggest cost savings we can. So, like, for example, in this graph, we see just a natural growth of tables in our data lake over the last few months. And this is at a pretty large scale. At the time of making this slide, there was around 35 petabytes of data in Iceberg format. This is continuously growing, and I'm sure it's at a higher number now. So this is really good for our company approach to adopt this data lake concept. So those were some of the benefits that we saw from adopting Iceberg, but it wasn't so easy. It wasn't. We ran into some challenges along the way and some learnings. So to go over some of these, first topic we'll talk about is some of the problems we had with actually using the dynamic schema feature. Then some problems we had with checkpointing. Downstream, we'll look at some of the query performance issues that we're seeing. And finally, just some learnings about how we didn't use hidden partitioning like we expected to. So yeah, we can move on to talk about the dynamic schema. So the biggest thing here is we were initially drawn into Iceberg. One of the reasons was being able to have this dynamic schema update. Then we found out that with the Iceberg Flink sync, right now it actually requires a static table structure. So this actually doesn't apply. We will have to restart our Flink job, change the logic, and have then we can have the Flink job update the schema in AWS Glue. So this is, at first this is sort of disappointing to us, but along with all of the other benefits we saw, it wasn't really a big deal. So this snippet here of code is just an example of how we modified the Flink logic to know when to update during a restart. And down below is actually something that we are really looking forward to, where I think there's an open proposal to make a Flink dynamic sync actually available. So this is something that we'll monitor, and hopefully it will be implemented in the future for Iceberg. So going to the next slide, that wasn't actually all the problems we had with the dynamic schema. So we changed the Flink job to be able to request the update on restart. But we found that it was actually still failing in certain cases to update the schema. And this is because the schema in Glue needs to match the schema that Flink is using, not just the field types, but also the ordering of fields. So we found that at times when we updated the schema, when Flink read it, it was in a different ordering. So we actually had to reconcile this and add some additional nested logic to make sure that the entire schema matches between what we're trying to write and the schema that exists in AWS Glue. Once we did that, we didn't have any more issues with updating the schemas, and we didn't have to worry about this anymore. So our next challenge, we are able to maintain the state pretty well. But then we saw at times, actually, some of the users of the tables told us that they are seeing stale data. They're not seeing the newest data they expect. We looked into this and we found that there were times where the data files were actually being uploaded to S3 from our Flink job, but the Iceberg file committer was actually not committing the metadata anymore. And originally we weren't tracking this. We added a metric, which is shown on the right, to track this sort of file committer commit by Iceberg. And in this example, it shows where all of a sudden it just drops to 0. It's still writing the data, so we weren't alerted. We didn't know about it. But once we add alerts on this metric, we see that, yeah, there is an issue for some reason. So why did this happen? Move on to the next slide. Yeah, so at the time for our Flink jobs, we were using 2 Flink job managers for this sort of high availability setup. And we found that when we, very occasionally, very rarely, or during some cluster upgrades, sometimes the job manager would fail, new job manager would pick up, but it would reset the so-called checkpoint ID that the Iceberg file committer was using. So let's say, for example, we were 1,000 checkpoints in. When the new job manager restarts, it will go back to checkpoint 1 for this Iceberg file committer. And the data files would continue to commit, but when Iceberg file committer looks at this, it thinks, oh, we're at checkpoint 1 or 2 or 3. We already committed it. We don't need to commit this. We're going to skip it. And it would do that until it gets back up to checkpoint 1000, where then it will start committing again. So for us, since this was such a rare issue for us, the easiest solution was to just have one Flink job manager. And this actually did resolve it. But yeah, possibly in the future, we will look, if we need to have more job managers again, we can look into how to actually address this issue. So let's move on to the next slide. So yeah, now we have our Flink jobs are running, and they're running successfully. They're working. We have the alerting set up. We did some query performance tests, and everything looked great. Actually, it was an improvement using our data lake. So either querying through Trino or querying through Snowflake onto the unmanaged Iceberg table. But then again, we got some requests from users saying some of my queries are actually running very, very slowly. We see a 2 to 6 times degradation. And we looked into this, and in all these cases, this was when a user was trying to query a large map. So this would be a field with maybe hundreds of key value pairs. And we had to look into why this is happening and how we could resolve this. So move on to the next slide. So we found that, yeah, this is pretty much a bad practice to do this. Rather than having just several columns for the data that you want to query, just having it all into one big field and then trying to query that. This was not an issue before because Snowflake had this variant data type, and this variant data type handled it pretty well. This type doesn't exist in Iceberg. So we had to find a solution for this. And there was 2 simple solutions. One is if you're commonly querying this huge field, we can pull out some of these very commonly queried key value pairs and make them a new column. And then when you're querying that, you won't have any more issues. So the other solution is, well, which is one that we actually took for most of our use cases, is that we already saved so much from adopting this Iceberg format. We can allocate some more resources when you're querying this, and it's really not an issue. Yeah, we can just, if we were using a large warehouse before, we can use an Excel warehouse. And this is the approach that we decided to take because it's just less invasive. So yeah, pretty funny. But yeah, we can move on to the next slide here. So this is really a learning rather than a challenge. So maybe I'll go over a little story here. So we have a data producer that is onboarding to our platform, and they want to track some order status in the DoorDash app. So they onboard to our data platform and they send data using some schema. Now we have someone else on the other side of the company, a data consumer wants to query this table and efficiently query it by timestamp, so using the partition values. Now this is assuming that they don't know what it's partitioned on, and a lot of times they really don't know this. We have thousands of data consumers, and not all of them are aware of how these tables are set up or how the workings are and how to find out this info. So let's say for this example, we have the top 3 fields are used in our sort of message envelope that is common to all events, and then an additional 2 timestamp fields that are attributed to the schema. So which field do they use? For someone who doesn't know how the event is set up or the nature of the data, it could be a challenge. And we found that in the past, when they have these challenges, a lot of times they try to reach out to us in our support channel and say, why is my query running so slowly? Can you help me? And we say, we just provide the event to you. We don't actually know the internal data structure, right? So we want to fix that. And maybe we move on to the next slide here. So yeah, the default partition that we're using is the Kafka timestamp. And we wanted to make this very clear to our users, just so to reduce the operational burden on us. So this is where we said, we're going to make new fields. It's going to be the partition date and the partition hour. And that's what you should use if you want to partition by the event timestamp. And we do this through a Flink transformation. And this helps us to reduce the actual confusion among the users. And it's sort of a different approach rather than the hidden partitioning, right? So that's why I bring this up. Rather than having this partitioning be hidden, we wanted it to be very explicit, just to reduce the confusion. Otherwise, for other partitioning use cases, like if they want to partition on some name or some other use case, we can then utilize hidden partitioning. But we found that we wanted, for at least the timestamps, to use a very standardized approach. I think those are all the challenges that we face. Yeah, talking about some of our future plans, we can move on to the next slide. So we want to, just continue integrating with Iceberg. Iceberg, we see it's constantly improving. It's open source community, and we want to continue monitoring and integrating any future improvements. Additionally, we also want to extend this integration not just for this pipeline, but for maybe other services we own or other teams that want to try improving their streaming capabilities. We still have thousands of pipelines that are not using Iceberg with the Flink sync. So we want to continue this migration process. It's a very long tail. And this big migration, who knows, maybe we'll use LLMs or AI to help us with this. But yeah, we want to continue getting these cost savings and continue really adopting Iceberg into our platform. So yeah, overall, it's been a very good process, and we've seen a lot of benefits. Yeah, we can move on to the next slide. Yeah, Gaurav and I would like to thank you for listening to this presentation, and we would be happy to answer any questions on the AMA.
Yeah, we have a lot of questions in here, so I'm just going to feed them out to you guys, and you guys just rebuttal your answer here. The first one up here is your data append only or upsert? And do you have to deal with equality deletes?
Yeah, that's a great question. So these pipelines specifically are append only. So this makes things a lot easier for us. If we had to deal with upserts, and some of our other sort of data movement services that our platform owns does have to deal with upserts. In which case they are also I believe they're also working towards adopting Iceberg anyways. So Iceberg is a good solution for this. So, but yeah, back to the original question. Yeah, we're append only. We don't have to worry about that kind of stuff.
What partitioning strategies have you found most effective for data, especially CDC data in Iceberg?
Yeah, like I mentioned, so we're append only, and we're not dealing with CDC for this service. But for partitioning, we found, like I mentioned in the slides, most of the use cases that consumers want to query their tables by are by the event timestamp. So providing them this timestamp date, timestamp hour for 95% use cases, maybe that's what they want, and that's good enough for them. We have a support channel, right? We monitor it, and oftentimes people will come in for requests to add more partitions or change the partitions for a specific event, which we can do because Iceberg, maybe we didn't highlight it here, but Iceberg also supports partition evolution, right? And that's another feature that is really handy for us. We can easily change that and accommodate any user requests.
Yeah, and just to add on to Tristan's answer, like we do have CDC, just not in this, like not in the real-time streaming platform. I would say it's a completely different service for which we use Spark and Delta still. Yeah, so I guess we just haven't explored CDC with Iceberg yet.
What kind of metadata tuning or file size strategies helped you guys reduce storage?
Yeah, so I think the slides mention right off the bat, Iceberg comes with this ZSTD compression. That helped us immensely. We also had to, of course, work with the sort of metadata maintenance, right? We had to make sure that everything is being properly maintained. So expiring snapshots or vacuuming and really what else, what other things that you do with the data files in S3, right? Rewriting the manifests to make it more efficient as more data comes in. I don't know, maybe
also do like, yeah, we also kind of rewrite the data files, right? Like to make them all an ideal size. I think the target file size we aim for is roughly like 120 MB. There's like a scheduled service job that runs periodically and kind of rewrites the files, come back to them. So yeah, that kind of target file size, along with some of the optimizations Tristan mentioned, we found works pretty well for us for the query performance.
How did you address the issue of small files in Iceberg when using Flink? Won't compacting those files cause conflicts when Flink CDC is writing to the same files?
Yeah, so this was again, this is we don't have to worry about this issue because we're append only, right? So this we were able to, like Gaurav said, have a job that will compact these small data files and make queries that much more efficient. So Gaurav, I don't know if you have anything you want to add to that, but we didn't see this issue on our end for this service.
Yeah, I think just due to the nature of kind of like our data, or like the type of rights we're having without, it's just not applicable for, I think, our use case. Yeah. Like we didn't meet this challenge. Yeah.
What are the primary use cases you have implemented with this architecture?
Yeah, so I think I mentioned earlier kind of what the downstream use cases are for real-time streaming, right? So I think like ML, like real time, like ML feature generation, for example, there could be downstream jobs that use a certain table as a source and generate features for our ML models using the data lake table, for example. Then there's also many like critical ETLs that for dashboarding and such that use our data lake tables, the Iceberg or even Snowflake in the past, and also just even ad hoc querying. There's just like a wide variety of use cases. Those are some like critical examples, but yeah, I think it just varies. Like basically, everyone in any like downstream engineering team in the company might be a consumer of the data that we produce.
Awesome. For cost savings, can you provide a percent reduction for storage and compute if you have any?
Yeah,
Happy.
I think that was provided in the slides actually. It's not the same for every event, right? It depends, but for storage, I believe the range was around 25 to 50%. And for the compute costs, at least compared with when we were using Delta, we saw some pretty massive compute costs up to like 70% at times for really over provisioned jobs. Yeah, hope that answers the question.
Awesome. What's the reasoning behind going with Glue Catalog instead of Polaris or something else?
Yeah, so I think at the time when we first went with the Glue, Polaris, we weren't familiar with Polaris, or it was just not available. I think it was introduced to us later after we'd already established the architecture, so we didn't explore Polaris too much. In terms of an alternative, maybe like Hive or something like that, I think Glue just attracted us because it's simple, it's managed by AWS, and it's kind of the least operational complexity. And we just didn't require some of the richer features that something like Hive might have over Glue. We just didn't need it. I think the simplest possible fit made sense for us.
Got it. Awesome. And we have about 60 seconds left. So unfortunately, that's all the time we have for questions today. I have captured all of your questions in the chat, and I will be sharing them with Tristan and Gaurav, and they can get back to you at their leisure. So thank you both for joining us. And up next in session 1, we're going to have scaling Iceberg adoption at Pinterest. So see you all there.
Thank you.